what it would be the ideal injection administration route and frequency for these types of therapies. I think that was one of the cool things I was reading about in your papers or in the lifespan post is that you can. Well, I'll let you answer the question, then I have a follow up question. I won't jump the shark. So yeah, what I can reread it.
Well,
What is the ideal injection? Go ahead. Sorry.
help me interpret the question. Is um, is your fan asking, like, do you have to inject it IV versus under the skin, or
Yeah, I think they're trying to discern like how would it be injected, and then how often to
right?
um to be effective.
Okay, yeah, it's a good question. And it highlights one of the distinctions of what we're doing versus a drug. So, in the history of drug design, we're in a new age of rational drug design, but that's not what most drug design has been for the last hundreds of years. Certainly, the last century. Most drug design has been done by correlation, where you have a molecule you know to be toxic, you throw it into cell culture, see if it'll kill a cancer cell. And if it does, you see if a mouse can survive it. And if it does, you see if a human can survive it and derive benefit from it. Um, and when they, and even today, when drugs are administered, even drugs that were developed with a more rational approach rather than just correlation, it's still based on hypothesis stemming from clinical trials that if you put this drug in at a given dose in a patient that has this cancer, you're likely to see a benefit. But it's only very rarely with certain drugs that there's anything to measure in the blood or even in the tumor that tells you whether that drug will work. There are some drugs where they know that there's a specific mutation in that specific cancer and the drug will be particularly effective because of that mutation. But most drugs, there's nothing you can measure in blood that's going to give you any insight into whether what you're going to administer is going to be effective. That's not the case with nanots, because remember, nanots are subtractive. All they do is take something out. Well, that thing they take out pre-exists in the blood. You can measure it. If it isn't present in a given patient, the nanot isn't going to do anything. So the first test, the inclusion criterion for that patient is the tumor generated immune inhibitor, basically the question is which tumor generated immune inhibitors are elevated, because that's all the nanots are going to do is take those out. And the ones that are elevated are the ones that that tumor is using to defend itself, necessarily. Can't survive without them. So, if you pick the main one that's elevated and you deplete that, and by the way, you can measure that. There's a off the shelf ELISAs, blood tests that will quantify that target both before you put nanots in, so it's the right nanot for that target and know what to dose it, how to dose it. But you can also run the same ELISA 30 minutes later to confirm that you actually depleted the target. And that's very different than drugs. This is called a proximal endpoint, meaning a first endpoint. The first endpoint here is, did the nanot actually do what it was designed to do? Did it deplete the target? And we know we've tested this repeatedly in rodents, and we know that pretty much every nanot will do what it's engineered to do. It will deplete the target it is engineered to deplete. It'll do it very quickly, within 5 minutes, typically, and very deeply, sometimes down to undetectable levels, but typically more than 90%. 95% is very common. The second endpoint is, do you see a clinical improvement? It's great to have that proximal endpoint. That's very powerful. Then you have to look for the clinical endpoint of improvement. And for that to occur, you have to have chosen your target correctly, and your understanding of the foundational biology has to be solid, that target is in fact a driver of that disease. Fortunately, we don't have to actually do a lot of that foundational science. It's been done for us. There's thousands of published papers by hundreds of teams all over the world on specific soluble targets that are known to drive different diseases or defend tumors. So we're just basically trolling the literature, absorbing all the information, the consensus that's already out there by all these great teams on soluble targets in blood that drive disease, and then we make nanots against those targets.
Check out the full video now and subscribe. It's free.